Hello and welcome. Today we're going to do a brief presentation on math and math notation. As we know, math is the not so universal language. So carrying on, like all good things, we start with some backstory. So I was sat in my math class taking a math exam and I came across this problem. This problem is not too interesting except for when we look at the middle bit. So we come in here, we see that this line goes like this, and then terminates right here. There's no arrow, there's no segment, but I believe it ends there. I am of the understanding that if this line looks something more like this, with like an arrow at the end, then that would go to infinity. However, my professor disagrees. She says that that line went to infinity without the arrow. This was really upsetting. I was thinking, that's ridiculous. So I talked to all my peers. I asked them, hey, can a line go to infinity without an arrow? And everyone I talked to said, no, there has to be an arrow. Because that's what we were taught in school, and that's what the schools are teaching us. So I'm starting to think, okay, my professor is wrong, but she just won't take a you're wrong as an answer. I need to bring some evidence. So I start doing some research. I come across René Descartes. René Descartes is a philosopher. He is famous for I think, therefore I am, and he, like a little lesser known though, is he's a mathematician. He's actually a really good mathematician too. He is the creator of the Cartesian coordinate system. And I think everyone knows this, but it's got a fancy name. It is just a graph. But on the graph, we can see that there's some arrows. And so I'm thinking arrows, graph. On the creation of the graph, there has to be some arrows. So I'll show her this, I'll get my point back. All this for a single point, by the way. So I look at his book, Logia Geometrica, and I find some drawings, and I see here, oh, there's some cute little arrows on here, right? Wrong. There were no arrows. I'm starting to think to myself, wait a damn minute. How could there not be any arrows? I'm starting to think, was I wrong? I knew I wasn't wrong. I couldn't be wrong. So I continued on my journey. I went all the way back, straight back to Euclid. Euclid is a famous guy. He's a mathematician. He's also referred to as the father of geometry. Who better to find out about geometry notation? So he wrote some books called Euclid's Elements. There's 13 books, and they kind of outline the basis of geometry. Kind of like some postulates, saying different things about math that be true. So they're kind of the standard for geometry. So they're highly respected. So I started looking at his 10th book, Definition 3. It states, with these hypotheses, it is proved that there exist straight lines, infinite in multitude, which are commensurable and incommensurable, respectively, some in length only. This means that some lengths have a commensurable distance, that is, some measurable distance, while others are incommensurable, meaning they stretch on to infinity. So this line, for instance, it wouldn't go on forever, which means that my basic understanding of how lines work was true. So now I'm in a weird spot, because on one hand, I'm not right, but I'm also not wrong. And it's the same deal with my professor. And this time, I got my exam back. I didn't even lose a point for that. I got a nice little X. But still, on principle, this was really upsetting, because I'm like, I know I'm right. There has to be some evidence that I'm right. So I do some more research. I'm trying to find, there has to be an example. I then try and go look at the school and the teaching. Why was I taught to use arrows? I couldn't find anything. I couldn't find anything in the Common Core curriculum. Couldn't find anything about it. I saw tons of examples with arrows. It just kind of was a thing. And I started to realize there's not a standard for these kind of things. People just use the arrow because it makes sense. It does make sense, personally, but some people don't use it because that also makes sense. That line just goes on forever. I can kind of understand. But this is not only a problem in this context. It is a problem in many other contexts with math and actually more complicated and more meaningful things. So with this understanding, I believe I have a solution to my problem and other people's problems, right? And that solution is the Committee on Mathematical Notation, right? It's to be a centralized standard for all math. All right, so let's get into some examples of when this committee will be beneficial. So first, we can talk about vectors, right? So vectors are a very hotly debated topic in math because there's so many ways to represent them. We have these ways, and actually, about the way I was taught, and first I didn't include this because I forgot about it. I realized is when I draw a vector, it looks something more like this, right? There's like 4 different ways to write a vector, and this is a two-dimensional vector. We can do the same for 3. And so it's the same thing as there's just different ways to do something when there doesn't have to be. And so a standard for all math would make it so that there was a single way to do it, and confusing nonsense like this would just disappear. Now that seems kind of, you might be thinking, this is kind of like stupid, it's just like one single thing, but bear with me, it gets a little bit worse. So now we can go on to variables for equations. So say we have this equation here, and in this equation, it includes this variable r. rs is equal to this, right? And what that means is that variable r is equal to this equation. Now you might be thinking, oh, that's really cool. And it is really cool, honestly. But what happens is this representation is not standardized, and so there are other representations that are all pretty similar, right? Like you might have like 10 out of 11 people will be doing it this way, but that 11th person might decide to do it a slightly different way, right? And by having it done slightly differently, will make this a lot more difficult to understand, as you'll be on your toes, wherever you won't be on the lookout, and you'll accidentally assume that something is what it isn't. So anyways, we can carry on to niche secondary forms. So here we have this equation, right? As you can see, we have exp parenthesis and then this bit. You might be thinking, what does that mean? It's actually very simple. It's just e to the power of what's contained inside that parenthesis. Why did they just put e to the power of what's inside the parenthesis? There is some understanding that that is a bit more simple to read, but at the same time, there isn't the need to create that confusion of what does that mean? Why is it that way versus just the way that is pretty standard for everyone to know. On we go to complex equations. We have a complex equation like this. There's a lot of parts to it, and that makes a very complicated explanation. So we have this explanation for how this equation works, and there's nothing wrong with this. I actually applaud this, that there's very in-depth detail about what this equation entails. So, but here's the issue. In a single field, there might be some agreement, but not really. And so there'll be slightly different variations of similar equations, enough to the point where it'll be the same pretty consistently, but then you'll have one outlier. Well, you'll bring those assumptions you made on the normal ones to that outlier, which will make you have bad results, failed understandings, just all around bad things. And this might happen maybe only once, but if it happens on some meaningful thing, that's unfortunate. Like, let's say you're trying to launch a satellite, and oh shoot, you messed up your equation just a little bit. That could have very serious implications. And that brings us right into our next point, which is computer science applications especially, but moreover, interdisciplinary implications. Because when you're trying to combine multiple disciplines into one thing, it's even more difficult. Because say you are really into astrophysics. I'd be willing to bet that you know almost all of the astrophysics formulas, and you'll be able to tell different ways some of those equations are written, and so you'll be fine. But say, oh no, you have to go see how, I don't know, some equation or formula is written for rocks, like just rocks. Maybe the rocks have a certain formula that applies, right? And what if they use a slightly different notation, right? Now your understanding of how that all works is a little bit skewed. So this is especially common in computer science, because here this is kind of a definition for how gravity works with time. And that doesn't seem important to an everyday person, but it is very important to how game engines run. And so what happens is you have these very complex equations that are very similar to normal equations that the computer scientists might see, But with some twists, they would have a weird definition in here, and like having things that are pretty common, like E, for instance, be assigned to like numerical eccentricity instead of Euler's constant, and so that makes it kind of more difficult to understand. So you might assume like, oh, it's E squared. No, it's not. And that's fine. I get that there's a lot of different things to process. But what happens is when you really start crossing these bounds and you really start going through tons of different equations with all these different definitions, it kind of just loses its value. So now all these things don't have value, which would help you understand things the way they are, but this makes it difficult to be concise and have a basic understanding of a lot of different things. So the way we could get around this is on like a discipline by discipline level, have certain variables and certain constants be referred to as like the same thing. And so if you're like, oh, you're using a biochemical equation, well, there's a chart for all the possible things you can encounter, and it's standardized. So every biochemical equation you saw would all relate to the same thing. So anyways, that is one massive implication that really would be affected with the standard. So anyways, got any questions about this? Anything that you would affect your life, or what are you guys thinking? Yeah, I had a question. I think that you're making a lot of sense, but my only question was about the interdisciplinary stuff. I think like more often than not, somebody would only use like a piece of an equation to put it in their simulation or whatever, and that doesn't really need you to understand the whole equation. Yeah, so that's an important question, and I think we can go back to like the example of a computer scientist. So we can go look at game engine development again. So say we're wanting to introduce like shadows into our game engine. So you're actually going to need to implement some of these equations in their entirety to get that to work, because it's just easier than recreating it all. And yes, they might be simplified, but to simplify an equation, you need to have a complete understanding of what's going on, because you can't make something different, or like more efficient, or like slightly less accurate but still accurate, because you won't know what to change to make it remain still tolerable, right? You gotta have that understanding. And so with this notation being different, it really creates a barrier to entry that makes it more difficult to get into this space and produce good work. Yeah, I'm more of the understanding that if you understood the source material enough, you'd be able to understand the symbols just by looking at them, just by simply being able to imply the meaning from the symbols alone. Yeah, so when you have symbols that have different meanings to different people, that's just going to cause confusion on a basic level. Because if you all aren't in agreement to what that you're trying to solve with your math, it's going to just cause time to be wasted. I guess it kind of goes back to the answer to the first one, was it just is a time saver to have all the notation be consistent, especially in things where you can't really mess up. Like I think shooting rockets is a big one. Like a really simple example of this notation being different, affecting things, is I think there was a rocket launch in 1999 where there was a conversion that wasn't done properly because they were doing feet to meters. They just messed that up, and that caused the whole rocket to explode. And I think it's a little bit harder to attribute an exact error to a notation, but I think saying that it wouldn't hinder development of such a project is kind of ridiculous. Yeah, just straight up, does there need to be a committee? I think this seems a little frivolous. Yeah, so I think you could say that we've gotten this far just fine. Why change it? And I think that is something when you consider with any progress. Like, we've done a lot with math. There's no denying that. But we want to think about how we can make math better in the future. It's like right now, it's going to be a big pain in the butt. People are going to have to change their ways, and no one likes doing that. But imagine a world where everyone was using the same notation to do the same things. That would be great. It's just a step forward. And as a civilized society, we have time to argue about things that aren't really affecting us like on a deep level. Like, this isn't going to matter if we're getting enough food to eat. This isn't going to affect that. But it will affect us in other ways. So I think that is why we're going to consider these implications. All right, thank you so much for the questions. Then we're going to wrap it up here real quick. So just in conclusion, we have the Committee on Mathematical Notation. That's what I'm asking you guys here today to consider. I think that this is just a natural step for humanity to take. I think that it would just be better to have a standard to abide by. I think that doing so would launch humanity forwards as a race. Thank you, and good night.